Hello, Earth Science kids. Listen, it takes some energy in the Earth's atmosphere to power everything you see that goes on in the Earth's atmosphere. So we need to talk about the energy in the Earth's atmosphere. Virtually all of it is provided by the light from the sun. We call light from the sun electromagnetic radiation. And if you look on your reference tables on the bottom of page 14, you will see the electromagnetic spectrum there. The important thing for you to know about the electromagnetic spectrum, as you increase wavelength, well, you decrease the energy. Electromagnetic energy is given off by a particle, a charged particle vibrating. So all atoms are giving off electromagnetic energy unless they're at absolute zero. And because almost none of them are at absolute zero, they're giving off energy, kind of exchanging it back and forth all the time. The hotter the particle, the faster it vibrates. Now think about if you have a cork in water and it's vibrating up and down. The faster it vibrates, the shorter the waves. Doesn't that make sense? Slow vibration, well, there's not much energy there. It would give off very long waves. So if you look at this electromagnetic spectrum on the bottom of page 14, you'll see really long waves. And what are really long waves called? Radio waves. Shorter, we get microwaves, then infrared. Finally, you get a tiny, 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 and I'm talking tiny, tiny, tiny band that we call the visible light spectrum. Visible light, the longest wavelength of it is red light. The shortest wavelength of it is what we call blue light. It's just your brain's way of coding for different wavelengths. Colors only exist in your brain. If you get shorter than blue light, now you're in the ultraviolet spectrum. Something is vibrating so fast it's giving off energy you can't see, but certainly energy that would affect you. Ultraviolet light is, of course, dangerous for you. Even more dangerous would be X-rays. If you get way too many X-rays, that would be very bad for you. And gamma rays would be even worse than them. And we're getting increasingly shorter wavelength and more violent electromagnetic radiation. So the sun gives off a huge range of wavelengths of electromagnetic energy, but you want to take a guess what wavelength it gives off the most of? Well, when you look around, aren't you making use of visible light? We evolved around this star. This particular sun gives off the bulk of its radiation right smack dab in the visible light spectrum. That's why we evolved to see visible light. It's the stuff that's around. Anytime a charged particle moves, it gives off electromagnetic radiation. Hotter the particle, faster it vibrates. Shorter the waves, more powerful the radiation. And the reverse is also true. So electromagnetic radiation in the surface of the Earth. Well, the atmosphere. The nasty radiation coming from the sun, all the ultraviolet X-rays and stuff like that, the atmosphere, very fortunately, filters most of that out for us. And it's a good thing it does, too. The ozone layer is the super protective part of the atmosphere that really shields us from the nasty rays. So most of the electromagnetic radiation we receive is in a narrow band we call visible light. I think I said that. Now here's something. Which particles move faster, the ones on the sun or the ones on the Earth? Obviously the sun. So which particles give off the shorter radiation? The sun. So visible light radiation coming from the sun is shorter waves. Well, the Earth radiates too, but it's not as hot. So it gives off much longer waves. This is infrared radiation. We call Earth radiation terrestrial radiation. And it's infrared light the Earth gives off. What happens to the energy is a separate thing. About 75% of the energy hitting the Earth actually evaporates water. Now, evaporation is going to store that heat from the sun. How can we make evaporation increase? It's a question you might be asked. Well, on a windy day or a calm day, which would evaporate a sheet, a wet sheet hanging on a clothesline? Which would evaporate it more? Obviously, a windy day. If it's warmer out, it'll certainly evaporate faster. If you have like warm tropical seas, they're evaporating mad fast. If you have cold polar ocean, that's not evaporating nearly as quickly. Well, if you can expose more water, that's going to evaporate faster, isn't it? So all of that will evaporate the water quickly. There are three states of water here on planet Earth. Ice. Ice, the molecules are held rigidly together. Okay? Is there much energy in that? No. It's at the lowest state of energy, which is why when you get water to be as least energetic as possible, you got ice. You get it vibrating a fair bit faster, now you have water. Now the molecules can move past each other, but they're still clumped together in water. But if you give it an enormous amount of energy, those molecules can come flying apart and they become water vapor. So if we subtract or add energy, we can change it from state to state. So for water to be changed from state to state requires energy to be added if going to a more energetic state, or subtracted if going to a less energetic state. For example, to turn liquid water to ice, you freeze it. It removes energy until it gets to 0 degrees Celsius, but it doesn't freeze. You've done this before. Put an ice tray in the filled with water in the freezer, and you're impatient. You come back an hour later. There's a little bit of ice on it, but it's mostly still water. It got to 0 degrees, but now you have to remove a huge, and I mean huge, amount of energy in order to get it to turn all to ice. So let's look at how this would work. All right. So if we have ice and I add heat to it, I can turn it into water. All right? I can add heat to it, turn it into water. What do we call that? Well, melting. If I remove heat from the water, I can turn it back into ice. What do I call that? Well, that's freezing. All right, I think we knew that. If water turns into water vapor, what is that called? Well, that's evaporation. Water vapor turns to water. We know that that's condensation. Okay, great. Well, did you know that water vapor can actually turn directly into ice? That's called deposition. Ice can also turn directly into water vapor, known as sublimation. Now, in all of these cases, it is involving tremendous energy exchanges. Just heating water up or heating water vapor up or heating ice up is one thing. But if you want to change state, it takes a lot of energy. That's why we put ice cubes in our drinks to cool them, because all the time that ice is melting, it's taking a huge amount of energy out of the liquid in our drinks, so it cools it down. Similarly, if you use water, if you put a really hot object in water and it vaporizes some of it, turns it to steam, that object is cold, the water isn't even hot. The vaporization of that steam took all that heat away. So that's how it works in this case. So fusion. Fusion is the change of ice into water or water into ice. This heat is called the heat of fusion. So heat is measured in joules. And if I want to turn water at 0 degrees Celsius to ice at 0 degrees Celsius, in other words, no temperature change at all, just turning the water into ice, I have to remove 334 joules of energy. If I want to melt that ice, I need to add 334 joules of energy. So the heat of fusion of water is 334 joules. And that's per gram of water. I need to either add it to melt the ice or remove it to make the ice. So we do see water vapor sometimes directly turning into ice without ever passing through the water phase. Look at that. Heat of vaporization. If I want to turn 1 gram of water at 100 degrees Celsius into water vapor, also at 100 degrees Celsius, again, no temperature change, I have to add, and look at that number, 2,260 joules of energy. This is why if you're wet, you come out of a swimming pool in a place that is very, very dry, you're going to be amazingly cold, because just evaporating 1 gram of water vapor or liquid water from you, turning it into water vapor, is going to require an enormous amount of energy. How much? Well, 2,260 joules. If I want to go back the other way, I have to remove 2,260 joules of energy. So when that cloud is condensing, Energy is being released to the atmosphere, and it's an insane amount of energy. The heat of vaporization of water is 2,260 joules. A lot of energy. So this diagram gives you a good understanding of things. Down here, leg A. All right, what's going on at leg A? All right, well, what we have is that this is ice. We're heating ice up. With the addition of a little bit of heat, the ice heats up very quickly, right? You see the temperature rise here. Once it has started to melt, the temperature doesn't change at all. As you add more heat, the temperature remains the same. So what is all that heat doing? Melting the ice, turning the ice into water. Once it's all water, when you continue adding heat, now the temperature rises. Okay, once you get up to 100 degrees Celsius, the temperature will not rise anymore. All that'll happen is when you add heat, you'll evaporate the water. You would call it boiling. So as you boil water, what's happening? Well, you're adding all this heat. The water temperature doesn't change. Rather, a lot of vapor is coming off. Water vapor. You're stealing the heat that you've added to that 100 degrees Celsius water. Any additional heat just comes off as water vapor. That water vapor is stealing the heat from it. Now look at this. All of this here. What two things are there? Well, you have water and water vapor. And you cannot raise the temperature until all the water has evaporated. Once you've evaporated all of the water, now you can raise the temperature of the water vapor. So, at leg E, what substance do you have? Water vapor. At leg D, what substance do you have? Two substances, water and water vapor. Excellent. Leg C, what substance do you have? Well, you're raising the temperature, so it just is water. At leg B, what do you have? You're adding heat, no temperature change. Must be two substances. This would be ice and liquid water. And at leg A, what substance do you have? Well, you're able to change the temperature, so it can be only one substance, and that's going to be ice. Specific heat, another important heat quantity. If you look on the front of your reference tables, page 1, you'll see specific heats of common materials. So specific heat is simply the amount of heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. So it's a small temperature change, and you're only changing the amount of 1 gram of it. So look at the specific heats, if you would, on page 1, and you should be blown away by something. Look at the specific heat of, say, basalt or granite. Basalt is 0.84, granite is 0.79. Okay, that's rock. That's how hard it is to heat up the rock. Rock doesn't heat up all that easily. Okay. Look at the specific heat of water. Water has a specific heat of 4.18. Nothing else on Earth comes close to it. Water has a huge specific heat. It takes so much energy to change the temperature of water, even a little bit. That's why long after it started to get warm out, after we melt the ice finally, long after it started to get warm out, if you're boating, you have to be very cautious on the water because the water is still so cold that if you were to fall into it, you would not survive a long swim in it. It would cause your body to start freezing up, and you would not be able to swim in that condition. So that specific heat, and water is crazy in the specific heat it has. That's also why, what do cars use to keep their engines cool? Please don't say antifreeze. Antifreeze is what we put in there mixing with the water so the engine doesn't freeze. Because if we have water in the engine block and it gets too cold, water, when it freezes, expands and it'll crack the engine block. So you put antifreeze, then it won't freeze up. Now, granted, antifreeze has a high specific heat, not as high as water. Water has the highest specific heat of anything around. It's a pretty amazing fact, too. Earth would be an entirely different place if water did not have these totally strange characteristics. So the specific heat times the mass times the change in the temperature is how you find out how much heat you need to change the temperature of a certain amount of water. So if you look at all these specific heats, gee, what thing has the least specific heat of any common substance? And you'll see, this is odd, it's lead. And lead is odd. If you ever hold a piece of lead, you'll notice it's not cold. Why? Well, if it starts off cold, sitting in your hand, it absorbs a little bit of heat from your hand and changes temperature just like that. If you put that same amount of water in your hand, it would be cold, and it would stay cold for a remarkably long period of time. Lead, on the other hand, changes temperature incredibly fast. Lead changes temperature about 33 times faster than a similar amount of water would. Odd fact. So water is the highest, lead is the lowest. Yeah, heard it here. Look at that. Look at that. Why does it do that? Why does a thunderstorm make such a big impact on the world? Why can it drop tornadoes that can rip towns apart? Where does it get its energy? Well, all the air that's rising, you see the flat bottom of the cloud? You see that flat bottom of the cloud? Okay, right here, that's the dew point. The rising air has reached its dew point. It all starts condensing above that. Whoa, a huge amount of energy starts being released. So much energy. A good way to think about it, take a pot of water, and ice water, okay? Put it on the stove, crank it up. How long until it starts boiling? Maybe 10 minutes. How long is it going to take, if it took 10 minutes to start boiling from ice water, how long is it going to take before you've evaporated the whole pot of water? If you've had any experience with this, you know it's going to take over an hour. So over an hour, all the energy you're putting into that pot of water is simply used to evaporate it. And all that energy is stored in that water vapor. Well, look at that cloud. Look at the rain coming out of that cloud. How many pots of water do you suppose are coming out of it? Every pot of water that rain cloud released that amount of energy, the same amount of energy it took to evaporate the whole thing, more than an hour's output from your stove per pot of water. So when you look at a thunderstorm and you're seeing all the stuff it does, that's not a surprise. It's releasing as much energy as a good-sized nuclear bomb would release. It's a huge amount of energy. Bam. Okay? It's what I'm talking about. Again, bam. So I think I've made a point here. Yes, indeed. So some specific questions. How much heat is needed to vaporize 3 grams of water at 100 degrees Celsius? Well, that would be the heat of vaporization. That's going to be 2,260 joules per gram. So about 3 times 2,260. Sounds good. How much heat is released when 100 grams of water vapor condenses? Again, we're looking at heat of fusion. So 2,260 joules per gram times 100 grams. How much heat is needed to melt 1 kilogram of ice? Well, that would be the heat of fusion. That's going to be 334 joules per gram. So how many grams is a kilogram? 1,000. So 1,000 times 334 joules. How much heat is removed to condense 3 grams of water vapor? Talking heat of fusion, heat of vaporization again. So here you have 7 grams of water times 2,260 joules for every gram. How much heat is needed to raise the temperature of 1 gram of water from 34 degrees Celsius to 45 degrees Celsius? Well, the change in temperature, we're talking 11 degrees Celsius, times the specific heat of water, which is 4.18 joules per gram degree Celsius, and we only have 1 gram. So 11 degrees Celsius times 4.18 joules is what you get. How much heat is removed when cooling 1 gram of basalt from 135 degrees Celsius to 130 degrees Celsius? Well, you're only cooling at 5 degrees Celsius, so that would be 5. And it's only 1 gram, so 5 times, well, what is that specific heat of basalt? 0.84 joules. So 5 times 0.84 joules would give you that answer. How much heat is needed to raise 2 grams of lead from 25 to 125? Well, you're changing the temperature by 125, or you're changing the temperature by 100 degrees Celsius. So it's 100 degrees times that 2 grams times 0.13 joules. That would give you that. So these are pretty easy. Hope you enjoyed this. See you next time.